This right here is my all new flash storage server. It's got 16 NVMe slots, 100 gig networking, an epic CPU, and all of it is completely water cooled. A server like this isn't something you'd typically find in a home lab, much less with off-the-shelf parts, but here you are, here I am, let's talk about it. So believe it or not, there was an actual goal or purpose to build this outside of making cringe YouTube videos. I've recently been self-hosting some AI workloads, and one thing that I've gotten interested in is how these AI backends handle KV cache, basically session memory for the model. Well, usually that's stored directly on the GPU, but what if it wasn't? What if it wasn't even on the same device? And you see where I'm going with this, right? Yeah, I wanted to see the effects of offloading KV cache to a remote server, and what I found through our testing is pretty interesting. Now, before we get into all that turbo nerd shit, let's talk about the build because, man, this was a cool one. And I feel like I say this every time, but this is my new favorite build. It's built inside a 2U Sliger CX2257G, which I'm pretty sure is the only 2U case that met my requirements, which were 4 5¼ bays and space for a water cooling setup. Now, the reason for the 4 5¼ bays were because of these guys in the front. And on the right, we have a 2-bay pump reservoir combo from AlphaCool. And I guess I technically could have found another spot for the reservoir and the pump, but the space just made sense. And the left side possibly contains the most important piece of hardware for this build. These are 2 separate 5¼ bays that hold 8 NVMe drives each. The top one does M.2 and the bottom one does E1.S. Each drive gets its own full 4 lanes of PCIe Gen 5 connected to the motherboard via MCIO. And most importantly, they're water cooled. I actually saw these when I was in Taiwan at Computex, so I reached out after to see if they'd send some over. They agreed to send one, so I bought the other, and surprisingly, they weren't that expensive. I think it was around like $250 for the M.2 one, which, I mean, that's still $250, but for what you get, I think that's pretty affordable. Yeah, these are freaking awesome. Each drive bay is hot swappable, and when installed, presses up against a cooling plate to keep the drives cool. And I'm pretty impressed with how well it works. I installed 8 of these Solidigm 15TB D5 P5430 E1.S drives. Yeah, roughly 120 terabytes of flash storage in here, and no, I don't get to keep them. Solidigm is sponsoring this build, so huge shout out to them for letting me use these drives for the build, but I have to send them back after this. Unless enough of you go down in the comments and say, whoa, Solidigm E1.S drives, that's cooler than a bear with knives. I don't know how that made it into the video. Anyway, these drives are part of your data center line, and I'll leave the specs here on the screen if you want to read through those, but the gist is that these are QLC drives designed to give you high capacity flash storage in a package that draws less power and is a bit more affordable. And yes, I know these are way too expensive for a home lab, but for data centers, not bad at all. We did put them in a RAID 0 array to give us as much bandwidth as possible, but for our remote purposes, the bottleneck is going to be our network or file system, which sounds funny to say when you have a 100 gig ConnectX-5 in here, but hey, this is flash storage. Now, I will note that these are PCIe Gen 4 drives, while our server is PCIe Gen 5. Not that it'll make a difference for our build, but the more you know. Now, the last 2 pieces of the build are the CPU and motherboard, and for those, we're reusing ones from our previous video, which is an 8-core EPYC 8024P and an ASRock Rack Sienna 8UD3 with 192 gigs of DDR5. I really like this motherboard because it has 7 X8 MCIO ports, which means I can easily connect 14 NVMe drives in here. The other 2 would have to be connected via Oculink or a PCIe card, but here's a secret. Come here. I don't have 16 drives running. Then to wrap it up, I have a flow sensor from Aqua Computer, a Bisky 4X 80mm radiator, an AlphaCool CPU block, and yet another AlphaCool pump. That's right, boys and girls, we have a dual pump system in here. I decided to do that for a few reasons. One is for redundancy. I didn't want one of the pumps to fail and accidentally kill the system, which I've done before. And 2, I wanted more pressure to get through those 2 NVMe chassis since they have thinner tubing and narrow fins. Oh, and it uses a Flex ATX power supply, which I have a 600-watt version. Okay, now I think that's everything. All the parts are listed down in the description, so if anything tickles your fancy, you can find it down there. Overall, I'm very happy with how this turned out. We squeezed a lot into a 2U chassis. That being said, if I did this all over again, I'd probably go with the 3U version. I think another 1U wouldn't really matter in terms of rack space, but it would go a long way for making everything easier to fit. And I could use full height PCIe cards. So yeah, for that one weirdo out there who's thinking about doing this at home, maybe go 3U. I don't know. All right, let's talk software and performance. The first thing I had to do was get our drives in a RAID 0 array and see if our cooling system is adequate. I ran a 5-minute stress test to the drives, a 5-minute CPU stress test, and both of them at the same time. And look at these numbers. That's wild. I figured our cooling system would work fine, but I really didn't expect it to work this well. Now, I'm aware that these are lower power drives and a low TDP EPYC chip, but still, the drive's barely breaking the mid-40s under a complete drive stress test is wild. And during our test, our server was sitting in my rack with pretty low ambient temps around 22°C, and with our dual pumps, we had no problems pushing 200 liters per hour. Even during my long-running caching benchmarks, the drives didn't even break 40 degrees. This makes me want to throw a higher power CPU in here and maybe 8 more M.2 drives to see what happens. Maybe in version 2.0, we'll see. Look how dense we have these drives together. That's 8 E1.S drives in like a quarter of this entire area. That's nuts. And usually you'd need super loud fans pulling like 20 watts each, and you still wouldn't see temperatures this good. Also, something to note is that these are just their regular old E1.S drives, not even their purpose-built cold plate drives designed for liquid cooling. And in terms of power, the entire system pulled around 130 watts at idle and around 170 watts when the cache was being hit. So for what you get, it's pretty dang efficient. Now, when it comes to our array performance, like I said, we're going to be limited by our 100 gig NIC for sequential I/O. For local testing, we got around 46 gigabytes per second reads and 20 gigabyte per second writes. That's 368 and 160 gigabit per second respectively. And for random reads, we got over 1 million IOPS, which is a lot and what you want to see coming from a caching server. It's just crazy to see numbers like this from a 120 terabyte pool running in my home lab. And my favorite part is that you can barely hear it running. It's awesome. So now that we've established that our storage pool is fast and nothing even gets close to 50 degrees, it was time to connect it all to my DGX Spark cluster and test out some remote caching. Now, what is a KV cache? I'm like 30 minutes into this video and I haven't even mentioned that. When an LLM generates text, it doesn't start from scratch for every single token. For every token that it's already processed, it stores a set of numbers called keys and values. That's the K and the V. And those numbers represent what the model has understood about everything that came before it. So without it, every time the model wanted to generate the next token, it would have to reread and reprocess the entire conversation from the beginning. Like, imagine if every time someone asked you a question about the book you were reading and you had to reread the entire book all over again. Gross. So instead, the model computes the KV cache during prefill, which is why powerful GPUs often have faster prefill where it chews through your entire prompt for the first time. And then it just reuses the cache for every token that it generates after that. Here's the problem. The cache has to live somewhere, and it's not small. For longer prompts or a lot of concurrent users, KV cache can easily consume more GPU memory than the actual model weights. That's what we are trying to avoid in this video. Instead of using up that expensive GPU VRAM, maybe we can leverage other options like system RAM and even remote NVMe storage. Now, if you're running your models with VLLM, that can natively spill over KV cache into system RAM when you run out of space, and that's awesome. But what it can't do is store your KV cache remotely and even share KV cache between nodes. Kind of. So this is where LM Cache comes into play. It's a caching tool you run alongside VLLM that adds the remote layer of caching and the P2P KV cache sharing between nodes. Let me clarify the P2P stuff real quick. If you're running VLLM with tensor parallelism where a single model is shared across all the nodes, then yes, KV cache is shared. But if you're running multiple instances of the same model, like behind a load balancer, then KV cache isn't shared at all. LM Cache fixes that in this scenario, and that's the setup we tested on. I spun up Qwen3 8B FP16 on all of our DGX Sparks to give us a mature, stable deployment to test with. With LM Cache installed on each Spark as well as our AI storage server, which was serving as a LM Cache coordinator, we had a tiered caching setup. Now let's explain those tiers. L0 would be the local VRAM on each node, and we intentionally kept this low because that was kind of the point. Don't waste precious VRAM on something we can offload elsewhere. L1 is the P2P level, so getting KV cache from another Spark. And here's where I need to clarify, in a more traditional AI server where you have multiple GPUs and dedicated system RAM, then that local system RAM would be your L1 layer, but Sparks use unified RAM, so VRAM and system RAM are the same thing. Next up is L2, which is moving to our AI storage server and using system RAM with the backends of Redis and Valky. Valky? I don't know. Finally, we have our L3, which is our AI storage server's big ol' NVMe pool via NFS over RDMA. The idea is that KV cache will be used in that order as space is available, and it kind of does, but not really in the way that we wanted. Spent a few days doing some tests assuming this was the case, and those tests showed that our local L0 cache hits are super fast, and everything else after that was slower but still on par or a bit faster than computing the cache over again. I was kind of okay with these results since the TTFT, or time to first token, or the speed, is only half of the benefit. The other is that you're not spending compute resources or using local VRAM. There are quite a few adjacent benefits to this, like less GPU compute, meaning less power and less heat, and then less GPU compute means you're freeing up GPU resources for other jobs or models. But after a little digging, I found two issues with our setup. One is that it wasn't even using our level 1 P2P sharing. It was silently failing and just skipping that step, which is why it showed being pretty much the same as L2 or L3. Looking back, that should have been obvious. After fixing that, we saw a dramatic change in speed for P2P, which is what we'd expect. The next one was that we then discovered that after we got our P2P working, the P2P and L2, L3 tiers can coexist, but P2P only ever gets hit for things that aren't in L2 or L3, even though it may be faster. The moment a cache block lands in Redis or on disk, L2, L3 wins every tie. I don't know if that's intentional or specific architecture design, but I'm not smart enough to figure that out. So looking at our overall numbers, it's starting to make more sense. L0 is the fastest, L1 is still pretty freaking fast, and L2 and L3 were roughly the same as recompute, maybe about 10% faster. Which may sound strange, but that's what we got. I think the fast RAM backend with Redis was slowed down by TCP communication, and in the L3 layer, the fast RDMA was slowed down by NFS overhead. So that means that there's really not much of a benefit to remote caching systems, right? Wrong. We haven't even mentioned one crucial aspect to having an NVMe backend KV cache. It survives crashes and reboots. Imagine you have gigabytes or terabytes worth of KV cache computed. Then you restart your server for updates or maintenance. If it's in a traditional setup where it's stored in VRAM or system memory, it's gone. You're back to recomputing it all over again. For the average user, this probably doesn't really matter. But what about for companies or data centers that are running tons of servers for hundreds or thousands of users? That's a huge win, not losing all that precious KV cache. And I actually tested this. I hit our setup with a standard set of model calls, then completely shut everything down, brought it back up, and hit it with these same calls and watched what happened. The calls were hitting the cache that was stored on the NVMe pool with a 100% hit rate, completely bypassing the pre-fill compute required to rebuild the cache context. How cool is that? So while it isn't any faster than recomputing in our case, the fact that it isn't slower, we can keep it on more affordable storage, and it survives reboots is still a huge net positive. And by the end of my test, I had over a terabyte of cache on the NVMe pool, so it's not out of the realm of possibility that our 120 terabyte Solidigm pool would be overkill for a medium-sized AI setup. I want to mention that most of my testing was done around TTFT because that's the clearest way to see the main benefit of KV cache hits, but it also does have an effect on overall token throughput. The more reusable cache you hit, the less pre-fill computation you have to repeat, which can improve TTFT and overall serving throughput. And this will greatly depend on the type of model you use, what caching tier you're hitting, and the kind of workload you're running, but I tried to make this as high level as possible, which probably sounds silly at this point in the video. All right, time to give my overall thoughts on this. In terms of the hardware, it's pretty freaking sweet. This is a server that I plan to make a permanent part of my home lab, even if I have to give back those sexy Solidigm E1.S drives. As for remote KV caching, I don't think we're going to be running that. Not because it's useless, but because it's just so overkill for a home lab setup. I normally run my Sparks with VLLM serving one large model, so the local and P2P caching is already built in. And I do want to revisit LM Cache again in the near future after some updates to see if we can get the entire full L0 to L3 cascading setup working perfectly just like we wanted, so I'll be monitoring that. What do you think about all this? Let me know down in the comments, and if you like this video, drop a like and subscribe if you want to see more Turbo Nerd AI stuff. I want to give a huge shout out to my YouTube members and my Patreons. You guys are my system RAM caching on a remote server that also spills into NVMe. Y'all are persistent. And if you're still watching, you're TCP. Thank you so much, and I'll see you in the next one.